I am Ijaz Ahmed. In this lecture, we shall discuss permutations. So we write definition of a permutation here. Definition, permutation. Let x equal to x1, x2, xn be a set with n elements, with n elements, then a bijection on x is called a permutation on x. Is called a permutation on x. So that means permutation is any bijection on a finite set X with n elements. For example, X is equal to, suppose, with two elements x1, x2, then a function f from x into x defined as f of xi is equal to xi for 1 less or equal to I less or equal to 2, because there are two elements in this set. So that means under this function f, x1 goes to x1 and x2 goes to x2. That means this function f defines an identity mapping on the set X. Similarly, for example, we can take another bijection on the set X as with elements x1 and x2. Then we can define a function g from x into x by g of x1 is equal to x2 and g of x2 is equal to x1. Then this function g is also a bijection on x, and these bijections on a finite set X are also known as permutations. Now we shall try to describe as what could be the number of bijections or permutations that can be defined on a set X. So our question is, what is the number of permutations on X, where X has the elements x1, x2, xn. So actually here we are taking a set with n elements, and we shall try to describe what is the number of permutations that can be defined on the set X. Now before going into the solution as what is the number of permutations on the set X, we shall only keep one thing in mind, that every permutation is a bijection, and a bijection sends different elements of X to the different elements of X. And we shall start the counting like this. Now if F is any bijection, if F is any bijection on X, bijection, or we shall use the term permutation, if F is any permutation on X, then F sends distinct elements of X, distinct elements of X to distinct elements. Now let's start with defining the images of these points x1, x2, xn under the mapping f. So let's start with x1. Now under the function f will send x1. It can send x1 into x1, it can also send x1 into x2, x1 could be sent to x3, and so on. The image of x1 could be anything in the set x1, x2, xn. So this implies the number of choices for image of x1 is n. So therefore x1 has n choices as its image. Now we shall proceed toward the second step. So this was our step first, where we defined the number of images for the point x1. Now similarly, in the second step, we shall try to describe what could be the images for the point x2. Now under the function f, x2 cannot be sent to cannot be sent cannot be sent to the image to f of x1. Now since the mapping f is a bijection and f of x1 is the image of x1, now f of x1 cannot be the image of x2. So suppose this f of x1 is equal to xi. This means xi, this gives xi cannot be the image of x2, because otherwise the function f would not be a bijection. So this means the number of images, the number of possible images for x2 is n minus 1. And in fact we can see that the image of x2 is any element of the set x minus xi, and this xi is the image of x1 under the mapping f. So therefore the number of choices for the image of x2 is n minus 1. Similarly, in the third step, we will obtain the number of images, in fact the number of possible images for x3 is n minus 2 number of possible images. So that means the image of x3 could be choose anything from the set with n minus 2 points. So continuing in this way, continuing in this way, what we see that the number of possible images for x r is n minus r minus 1. So combining all these things, this concludes that thus we conclude that the total number of bijections on x is n into n minus 1, and this n is the number of images that can be chosen for x1, n minus 1 is the number of possible images for x2, and similarly here we have n minus 2 as the number of possible images for x3, and so on. Similarly, the number of possible images for xn minus 1 is 2, and the number of possible images for the last element xn would be equal to 1, and this number is actually factorial n. So therefore, the number of bijections that can be defined on a set X with n elements is n factorial. Now we write some notations. So let's have some notation. The notation is about the two-road notation or two-road representation of a permutation. So what it means by writing the two-road notation for a permutation? If X is a set with elements, suppose x1, x2, xn, and f is a permutation on X. F is a permutation on X, then F sends different elements of X to different elements of X. Then we can express F like this. Then we can write F equal to, in the first row we will write the elements of the set X. So it's x1, x2, x3, so on, xn. And in the second row of this presentation we will write the image of xi below the point xi. So here we will write the image of x1, that is f of x1, and under x2 we will write the image of x2, that is f of x2, and similarly here we will write f of x3, and so on, and here we write f of x1, xn. So this is the two-row notation for a permutation. For example, if we take the set X with two elements x1, x2, and f of f is a permutation on X, f from X, and X is a permutation defined by f of x1 is equal to x2 and f of x2 is equal to x1. Then we can write this permutation as, f as, so here we have x1, then here we can write f of x1, and here we have x2, here we will write f of x2. Now this is equal to x1. Now the image of x1 is x2 under f, and similarly here we write x2 and the image of x2 is x1 under f. So this is the permutation f that can be written in a two-row notation. We take one more example here. For example, assume the set X to be the set 1, 2, 3, 4, and G is a permutation on X. G is a permutation on X defined by G of I is equal to I plus 1 when 1 is less or equal to I, less or equal to 3, and G of 4 is equal to 1. Then this G can be written in a two-row notation as, in the first row we write the elements of the set X, that is 1, 2, 3, 4, and in the second row we write the images of these elements. Now as we have defined, there is G of I is equal to I plus 1, so that means G of 1 is equal to 2, so we write 2 here. Now G of 2 is equal to 3, G of 3 is equal to 4, and we have defined as G of 4 is equal to 1. Now we shall proceed towards having some more notations. One more notation we will introduce here. Notation. Thus, if order of X is equal to n, that means X is a set with n elements, then the set of all permutations on X is denoted by Sn. So that means Sn is the set of all permutations on the set X. Now, as we have already seen that the order of this Sn is actually n factorial, where n is the number of elements on which these permutations have been defined. Now we proceed towards one nice theorem in abstract algebra. The theorem is Sn for n greater or equal to 1 forms a group. Forms a group under composition of functions. Under composition of functions. So the operation under which the set Sn forms a group is the mapping composition of functions. So the proof is actually simple. For a set Sn to be a group, we need to check 4 properties. The first property is that we need to check that this Sn must be closed under this mapping composition now. This Sn should be associative. It must have an identity and every element must have an inverse. The first property is Sn is closed. Sn is closed because given any two bijections or permutations, given any two permutations f and g in Sn, then f of g and in fact g of f is also a permutation. Therefore, whenever we have two elements f and g from Sn, then their mapping composition is again a 1-1 onto mapping or a bijection. So that means the composition of any two functions is again in the set Sn. The second property is Sn is associative. Sn is associative. And the associativity of Sn comes from the associativity of the set of all mappings that can be defined on the set X. So we write the conclusion like this: since all mappings or functions, all mappings are associative on a set X, thus in particular the set of bijections is associative. So therefore the set Sn is also associative. Now third, as the identity mapping is bijection on a set X, thus, and this function, this identity mapping satisfies and we know that this identity mapping satisfies one, suppose one is the identity mapping, then one composition with f is same as when f is composed with 1, the identity mapping, and this equal to f. So that means this identity mapping works as an identity element of the set Sn. So therefore the set Sn also has an identity. Now the fourth conclusion is each element of Sn has an inverse. And the conclusion follows from this fact, since each element of Sn is a bijection And we know that a function has an inverse if and only if it is both 1, 1 and on. Now since each element of Sn is a bijection, thus every element of Sn has an inverse. And we have that Sn is the set of all permutations on the set X. Therefore, and every element of Sn is a bijection, therefore its inverse will also belong to the set X. That is, for all f belonging to Sn, there exists G belonging to Sn, and in fact the inverse of every element is unique, so we can write there exists a unique G belonging to Sn such that f of G is equal to G of f is equal to the identity mapping. Therefore, the set Sn satisfies all the four properties of forming a group. Therefore, the set Sn forms a group. Thus, Sn is a group under composition of mappings. Under composition of mappings. And we have earlier seen that the number of elements in the set Sn is n factorial. So we can add a note here. The order of Sn as a group is n factorial. In this lecture, we shall discuss only these things. Now we shall come towards the symmetric groups S1, S2, and S3 with some examples and some more things in our next lecture.